In the last two lectures, we saw how log-Sobolov inequality is connected to a classic information theoretic inequality called the Stamps inequality. This was the connection between Gaussian log-Sobolov inequality and Stamps inequality. In the next two lectures, we will see the connection of Gaussian log-Sobolov inequality with another very interesting notion, namely that of Gaussian hypercontractivity. In order to talk about hypercontractivity, I should first describe contractivity. In particular, I should first talk about contraction. So this is a quick review. I will not spend too much time on this, and I will not be very formal. So roughly speaking, a mapping F on a metric space is a contraction if it shrinks distances. So if the distance between f of x and f of y is less than equal to distance between x and y, then f will be a contraction. Okay. So this is what a contraction is, because it shrinks distances. Okay. And in fact, if this underlying metric is if this underlying space is not only a metric space but it has a norm, then it suffices to talk about the norm of f of x. By the way, this distance can be some other distance. If you want, we can have something on d prime instead of d, because f will take you to a different metric space. Similarly, this is a different norm. Okay. Suppose this is less than equal to norm x, then for all x, then implies f is a contraction. So that's what a contraction is. Okay. And in this lecture, we'll be interested in a very specific mapping, namely the so-called Markov kernel. And let's begin by showing that the Markov kernel is a contraction. So before we talk about hypercontractivity, let's talk about contractivity of the Markov kernel. Okay. So what's the Markov kernel? So consider two random variables x and y with joint distribution pxy. Let f be a mapping from x, that's where this x takes values, to r. Okay, so f is a real valued mapping. I'll put some, rather than putting constraints on f up front, I'll put this constraints as we move forward when we require them. So we are given this mapping f. Using this, we can describe a mapping on y as follows. So define G, which is now a mapping from y to r, as G of y equals to the conditional expectation of fx given y. I abuse the notation and write y equal to y. So this is basically this is a random variable, and this is a realization of that random variable. Okay, that's my G of y, the conditional expectation. Okay, so this operator we'll use w to denote by w the channel py given x, or maybe x given y. Okay. And with an abuse of notation, we denote the operator that converts f to g by w. Okay, so what we have seen here is basically g equals to w of f. Okay, so that's the mapping. So this operator w can be thought of as is called Markov kernel. Okay, and we will show that this Markov kernel is actually a contraction. So to talk about contraction, we should first think of a basic norm for random variable. So let's use, so that's the claim w is a contraction for we will use LP norm. Okay, LP norm. So what's the LP norm? So how do we prove this? Firstly, what is the claim? So claim is follows. That is, if you look at the random variable g of y, look at its LP norm. What is the LP norm of g of y? This is the expected value of g of y to the power p. Claim is this guy is less than equal to, so this is, by the way, this is norm of w of f is less than that's correct, is less than equal to the LP norm of f, which is expected value of f of x to the power p to the power 1 by p. Okay, that's the claim. Okay, so how do we show this? Well, the proof is actually not so difficult. The proof is just Jensen's inequality. Okay, so let's see. So the LP norm, this LP norm to the power p for this is simply expected value of f of x given y to the power p, and this is less than equal to, if we take this expectation inside, right? This is by Jensen's inequality. Actually, this is sometimes called conditional Jensen's. And now this is, as we have seen several times, this is exactly equal to expected value of fx to the power p. Right. So that's the proof. So indeed, this is a contraction. Okay. And right. And so what we will show is that, in fact, we will see that this inequality can be improved, can be strengthened for many distributions pxy. Okay, so the fact that this inequality holds for all, this inequality here holds for all functions f, okay, fact that Markov kernel is a contraction, that's a feature of the distribution pxy. It depends on the joint distribution pxy, and the claim here is that it can be strengthened. Okay, so that's what, and this strengthened inequality is called hypercontractivity. So you see that you are, in a sense, improving Jensen's, and whenever you can improve Jensen's, you can have very, very interesting deep consequences. So now we'll talk about the hypercontractivity of the Markov kernel. Okay, so let's bring in a definition. Uh, so this Markov kernel is associated with a joint distribution. So we'll just talk about a joint distribution. A joint distribution Pxy is PQ hypercontractive. Okay, PQ hypercontractive, where Q is actually is smaller than or less than or Q is less than or equal to P, and so we are ruling out P being infinity and 1. Okay, previous bound also holds for P equal to 1, but we are ruling out those things. If this is just for convenience that we are ruling it out, it's not so useful if P is equal to 1. If you look at the Markov kernel associated with Pxy, and you take any function f like this P is less than equal to this Q for all functions f which have finite qth moment. So this is basically functions f which lie in this space. Okay, these are the functions which have finite qth moment. So that's when we'll call it P. So why is this stronger than when can it be stronger than hypercontractivity? When Q is strictly smaller than P. So note that if Q is an increasing function of Q, therefore the previous inequality is stronger than contractivity when Q is smaller than P. And in fact, we would like to find as small a Q as possible. So this is the inequality that we want to prove. And note that if this inequality holds for a Q, it holds for all Q prime greater than that Q because of this monotonicity. Is an increasing, I should say non-decreasing, not increasing, necessarily increasing. Okay, so let's define the best Q. Okay, so let SP for this joint distribution, it's a function of joint distribution, but it's maybe I'll just write it as Pxy is defined as, actually, I think this notation is slightly better. So I'm viewing it as a function of the random variables, but it's a function of the joint distribution. But this is for convenience. This is how we indicate even sometimes in mutual information and information theory as a function of random variables. But it's a function of the joint distribution. So we will define this guy as the infimum over Q by P such that such that Q is smaller than P, Q is greater than 1 and smaller than P, and Pxy is PQ hypercontractive. Okay, and the point is that we get an interesting, more than interesting actually, inequality when SPxy is less than 1. Can you make it strictly smaller than 1? Of course, it's already clear that it's less than equal to 1 because any Pxy is PP hypercontractive, because PP hypercontractivity is just contractivity, and we want to check if it can be made less than 1. Okay, that's hypercontractivity. There are many equivalent forms of the same requirement, this inequality, and we'll present that. Okay, so let's do that. Equivalent forms. Simplification. Okay. So first, we note that WFP is less than equal to FQ if and only if expected value of Fx gy is less than equal to F so F P prime G Q, okay, for all functions G which have a finite qth moment. This function is of y, where this P prime, by the way, is the Hölder conjugate. Hölder conjugate this. So 1 by P prime plus 1 by P equals to 1. Okay. So that's what P prime is. Okay, so how do we show this? Proof is easy. This is just Hölder's inequality. Suppose this holds, then expected value of Fx gy equals to expected value of Wf of y gy, because this is the conditional expectation, and g when you take conditional expectation given y, gy comes out because it's a constant given y. Okay, and now we apply Hölder's inequality, so that gives us Wf okay, maybe a small change here. So this will be P prime and this would be Q. Yeah. So Wf of P and G of P prime. Right. And now this is by Hölder's inequality, and now this is less than equal to FQ GP prime. Okay, so this is an improvement of Hölder's inequality because you have replaced this pth norm by p prime here. You could have applied Hölder's and you would have got p prime. Directly you could have applied it here. But this is smaller than that. So this is a smaller value. So you have improved Hölder's inequality. Okay. So this direction is done. How about the opposite implication? So this shows that hypercontractivity implies this new form. By hypercontractivity of W. And now for the other direction, suppose this inequality holds for all G, then consider F in LQX. Okay. Okay. That's what we need to consider here. So if we look at such an F and we look at expected value of WF to the power WF y p, the pth moment, this is equal to expected value of WF y times WF y to the p minus 1. So this is exactly equal to expected value of fx given y WF y p minus 1. So which can be also written as expected value of fx times WFY p minus 1. And now we use the other form of hypercontractivity, with this being G, and note that this is indeed we can view this as G, because note that expected value of WFY of, so this is to the power p minus 1. Suppose we raise it to the power p prime. So that's p by p minus 1. Okay, equals to expected value of WFY to the power p, and that guy here is less than, this is the contractivity property we saw earlier, fx to the power p, and that's less than equal to fx to the power p. So maybe we should assume this f is in p. Okay, and this is finite. This is the assumption here. Okay, therefore WF belongs to L p prime y. This was a requirement here, by the way. And therefore we can apply Hölder's inequality. So expected value of, we can apply that improvement that we are assuming here, WF. If you're lost, what we are trying to show is this inequality implies this inequality. Suppose this inequality holds for all function G, then this must hold. So this guy here is less than equal to FQ and WF P prime. Okay, but that's the same as, so this is FQ and this is now WF P prime. But what is this? This is exactly equal to this. So this guy here is WF P to the power P. Okay. Sorry, WF to the power p minus 1 p prime norm of that. What is the p prime norm of wf p minus 1? We just saw this. This is exactly equal to wf p to the power p by p prime. Okay, that's this norm here. So what we get is, this is the same as saying w f p to the power p into 1 minus by p prime less than fq, and since p prime is the Hölder conjugate of p, so 1 minus 1 by p prime is 1 by p, so this is just 1, so which is the same as saying wfp is less than equal to fq. Okay, so this is a standard way of expressing these norm inequalities in terms of this inner products here. Okay, so you may have seen it in functional analysis where you show some bound holds for all test functions in this class, then the same bound holds for all function. If this holds for this, then this also holds. Yeah, these kind of tricks are used, and we have chosen G carefully here, but it works out. Okay, so in other words, we see that this particular form of hypercontractivity is equivalent to this strengthening of Hölder's inequality. Okay. The next simplification that we introduce is the familiar tensorization property. So if we want to establish hypercontractivity for product measure, it suffices to show hypercontractivity for individual coordinates. In particular, remember this quantity SPXY was defined as the least value of the ratio Q by P, such that this joint distribution PXY is this is the least of all Q greater than exceeding 1 but less than equal to P, and such that PXY is PQ hypercontractive. Okay, we had defined this quantity. Now suppose you want to evaluate this quantity for product measures. So xn and yn denote two independent distributed random variables. So let's say xi yi for I equal to 1 to n are iid pxy. Then the quantity sp of x and yn, which must be less than 1, is equal to max over 1 of I over 1 to n of sp of xi yi. Okay, this is the so-called tensorization property. In particular, if they are identically distributed, then sp of x and yn equals to sp of xi yi. So how do we show this? I'll present a proof, sort of an old proof of this result from a paper by Alsvida and Gach. A little less known paper, but it's one of the initial papers looking at hypercontractivity. So this is how they prove it. Note that it suffices to show this for n equal to 2. And that's what we'll do. We'll fix n to 2. So we need to show that sp of xn x2 y2 equals to, this is what we need to show, max of sp of x1 y1 sp of x2 y2. Let's call this guy something. Let's call it R. The max, we're denoting this max with R. Okay, so how do we show this? uh, so consider a function f from x1 cross x2 to R, and denote w2 equals to w1 cross w2. So two channels applied independently. That's what this w2 is. It will be applied to the function f. The condition, so we'll use this w2 operator as before. W2 of f will be the conditional expectation of f given y1, y2. So this is again y1, y2. W2, this is expected value of f of x1, x2 given y1 equals to small y1 and y2 equals to small y2. That's the W2 operator. And maybe one more convenient notation. If you have a function, say g, for a function g which has two arguments z1 and z2, we define g subscript z1 as a function of z2 as g of z1 z2, and similarly g z2 of z1 is g of z1 comma z2. Okay, this is just for convenience. Okay, so all the notation is set. So what do we want to show? Let's look at so we show that expect that for all f that are think an LP, expected values W2 of f p is less than equal to f of rp. Okay, that will complete the proof. Yeah, I'm being a little bit informal here. There's an inf in this definition, and I'm treating it like a min in the sense that I'm thinking there is indeed a number for which there's indeed a q for which this is qp hypercontractive. You can make it formal very easily by replacing this r with r minus r plus epsilon, and then taking limit epsilon going to 0. That's the standard way of handling this inf and soup. So I'm not bothered about that. So we'll show this. How do we show this? So let's start with this conditional expectation. Conditional expectation of f x. So x here denotes the vector x1, x2. Maybe it's better to write the whole thing, y1, y2 to the power p whole to the power whole to the power p. Let's look at this guy. This can be written as expected value of, so here the expectation is over x1. So expected value of f of w2 of f of y1, y2 to the power p. I will write it as y1 y1 of y2 to the power p. Okay, this is f of y1, y2. I'm w2 f of y1, y2. I'm using a notation here to simplify it this way. Okay, And what is this quantity here? So for each y1, this guy here is simply expected value of the pth norm of this guy. This expectation is over y1 outside this point. So the functions are different, but for each of these random variables, which is just dependent on y2 now, this is this expectation. Okay. So now let's focus on this quantity here. So for this quantity, we note that this W2 of f of y1, its pth norm, this is equal to expected value of, so y1 is fixed in this part, so maybe I'll use a small y1 here. So then this is equal to expected value. This expectation will be over y2. W2, the conditional expectation of f of x1, x2 given y1 equals to y1, y2. This is my random variable whose expectation I'm taking over y2. So this random variable to the power p whole to the power 1 by p. Okay, that's what this quantity is. There's another power, we'll come back to that later. And so this part here, if you look at this inner part here, it can be viewed as expected value of, so let's make some space, 1 by p. And let's look at this inner expectation here. There's something to the power p. Okay. So what is this inner expectation here? So this inner expectation is over x1. Is over x1 and x2, but let's look at the expectation over x1 part. So that's looks like this is the conditional expectation. So we'll do d of, this is notation for convenience so that things become explicit. This is the conditional distribution given y1 on x1, and it doesn't depend on y2 because of independence. So we can just do this part, and we have expected value of f of x1 x1, so this part is f of x2. Now if you look at this particular conditional expectation, you have to average over both y1, y2, but there is no dependence. So given y2, x2 is independent of y1 and x1, and therefore we can only write it as this. So once again, the point here is that this inner part can be written as W2, just the W2 operator, not the superscript 2, the second channel of f of x1. That's this conditional expectation evaluated at y2 evaluated at y2. That's the random variable we have. T of p x1 given y1, and what we are looking at is the, so this is a function of y2, and we are looking at the LP norm of this random variable, Now by Minkowski inequality, this is less than equal to the LP norms of individual guys weighed by this thing. Okay, this is Minkowski inequality. Okay, because this is just the fact that LP norm is a norm, and this is roughly the triangular inequality for LP norm, which is called Minkowski inequality. Okay. Now here, once we have this part, now we can see that this part here only entails the W2 function for the second channel, and therefore by using definition of R and the fact that the second channel is PRP hypercontractive, this is less than equal to f of x1 x2. Okay, that's the function here given qth norm of this, that's sorry, rpth norm of this. Okay, that's what this green expression here can be bounded, and we have used now the hypercontractivity for the second coordinate. So we'll substitute this guy in this form here. So on substituting, what we get is, let's maybe zoom out to see both of them at the same time. Right, so we'll substitute this in this guy here. So therefore expected value of W2 f of y1 y2 is less than equal to expected value. Now I'll substitute this guy. This is just the conditional expectation given of x1 given y1, and then there's an expectation over y1, so that's just expectation over y1. And this whole thing to the power p, so that's conditional expectation of fx1 x1 x2, the rpth norm of this random variable, this expectation given y1 whole to the power p. Okay, that's what we have, that's where we have reached. Okay, so we've already used hypercontractivity for the second coordinate, and now it's time to use hypercontractivity for the first coordinate. So towards that end, this is less than equal to, so now we apply hypercontractivity for the first coordinate. You see, this is exactly that form. This is exactly equal to expected value of, we'll think of this function as some, we'll name this function something. Let's call this function here as this norm already takes expectation over x2, and this is only some function of x1, so we'll call this h of x1, okay, or maybe g of x1. And so this is just w1 of g evaluated at y1 to the power p. That's what this is. And now using hypercontractivity for the first coordinate, this is less than equal to g of x1 rpth norm to the power p. Okay, which implies that w2 of f pth norm is less than equal to gx1 rpth norm. This is where we used hypercontractivity for the first coordinate. So let's expand what this g looks like. So what is its rpth norm? That's expected value over x1 g of x1 to the power rp and whole to the power 1 by rp, and then this is equal, what is g to the power rp? Well, this is g of x1 is this norm to the power rp, so that's f of x1 x2 rp to the power rp. So what is this inner norm? This inner norm is nothing but expectation of f of x1. This expectation is over x2 and this one is over x1. to the power rp. Given x1, just to be explicit here, and this is nothing but f of x1 x2. This is just f of x1 x2 to the power rp. Okay, so essentially we have obtained. Okay, all right. So that's what we get. Okay, and this exactly shows that this SP of x2 y2 is also less than equal to r. Okay, and indeed SP of x2 y2 must be greater than equal to r, because we can consider functions which are just depending on one coordinate, and for them the hypercontractivity coefficient, the best one here, will depend only on the will equal the hypercontractivity for that coordinate, and so SP x2 y2 must be greater than equal to max of SP x1 y1 and SP x2 y2. Okay, so this must be equal to r. That's the proof. The proof was a bit tedious because of notation, but I think this is a very delicate proof. For example, here, instead of taking the pth norm, if you take pth norm to the power p and used Jensen's inequality here instead of Minkowski inequality, then you will not get this bound. You will get a weaker bound, which will not give you this hypercontractivity. Okay. So long story short, this SP tensorizes. It's just max of each coordinate. Okay, so great. So if you want to show hypercontractivity for product distribution, it suffices to show hypercontractivity for individual coordinates. This is something we have been doing for other inequalities as well, and it's good to see that it works for hypercontractivity too. Okay. All right. So this was the second simplification. Now, third simplification. So from here on, before we go to the third simplification, so where are we currently? Let me take a bigger erase. So from here on, we focus only on the one-dimensional case, because by tensorization the result for general dimensions follows naturally for product distributions. Okay, now third simplification. This is very interesting. This one will relate hypercontractivity to so-called strong data processing inequality. So we have seen tensorization, we have seen this alternative form, and now we are seeing that in fact you can relate hypercontractivity to strong data processing inequality. So recall the data processing inequality. If you look at divergence between WP and WQ, these are the output distributions when the input distributions are P and Q passed to the same channel. This must be less than equal to dpq. This is the Kullback-Leibler divergence. This inequality is called the data processing inequality. In fact, the same inequality holds for a larger family of divergences. So let's introduce that larger family. The same inequality holds for so-called Rényi divergence. So what is Rényi divergence? So what is this Rényi divergence? So Renyi divergence of order alpha between two distributions P and Q, let's say P that's absolutely continuous with respect to Q, so it has a density with respect to Q, is given by d alpha. So this alpha here is something that's greater than 0 but not equal to 1. PQ 1 by alpha minus 1 log, let's say natural log, expected value of, so P has a density with respect to Q, take that density and take its alphath part, alphath moment. So this looks, yeah. So this is what Renyi divergence is, and for discrete case you can simplify this. P alpha PQ for discrete case can be written as 1 by alpha minus 1 summation, let's say distributions are both on x, log summation x px, so px by qx to the power alpha into this expectation with respect to q, that's the bigger measure, qx into qx, so you get px to the power alpha qx to the power 1 minus alpha. Okay, you may have seen this form, but yeah, this is Renyi divergence, expected value of this dp to the power alpha. Okay, so just like Kullback-Leibler divergence, you can show, this is not a difficult proof, this Renyi divergence also satisfies data processing inequality. So d alpha wp wq is less than equal to d alpha pk. This is also true. Okay, so that's true. So now suppose pxy is pq hypercontractive, where p is where q is less than equal to p. Suppose this is true. Then consider this function. Consider f(x) equals to d p by dq. Okay. Then d so we have to make an assumption. We have to consider this such that and assume that the pth norm of fx is finite. Okay. So what do we have? By hypercontractivity, since this PQ hypercontractive, W of f, the pth norm, is less than equal to f qth norm. Okay. So what is this guy here? Well, let's take log on both sides so that we can relate it to divergences. This is less than equal to log of f of q. And let's make this Rényi divergence. So which is the same as saying that, so this right side here, this guy here is exactly equal to q minus 1 into the qth linear divergence between p and q. But what is this left side? We'll see what this left side is. Okay, so note that this w of f of y is equal to conditional expectation of fx given y equals to y. So what is this guy? This is the conditional expectation of dp by dq given y equal to y. So what is this quantity on the right? We claim that this quantity on the right, expected value of dp by dq, which is a function of x actually, given y equals to y, is exactly equal to, it's almost surely equal to, the density of the measure wp with respect to wq. Since p has a density with respect to q, the output distribution when you pass through channel w also has a density with input distribution p, also has a density with respect to this wq. If that density is exactly this conditional distribution. Now this proof is a bit technical, but we will just show it for the discrete case where it's easy to see. So for when x, y, when random variables x, y are discrete. In that case, expected value of dp by dq as a function of x given y equals to y equals to summation over x. By the way, this expectation is with respect to q, qx. This ratio is px by qx. So density is just px by qx. And you want to look at this probability of, you want to look at probability of x given y. That's probability of xy. It's qx into wy given x by probability of y. What is probability of y? Probability of y is simply summation over x qx w of y given x. Let's write it slightly better. This is equal to px by qx, that's this function, times qx wy given x divided by the marginal, which is this guy. Okay, that's what the density is. But if you look at this guy here, this is the probability of y under w, and if you look at this guy here, this qx cancels, so that's probability of y under p by probability of y under q. This is essentially, this is exactly equal to wp. Okay, so indeed this conditional expectation is equal to this density, and this can be proved in general under some conditions on the channel, some technical conditions on the channel. We will not get into all that. The way I know how to show this proof is by defining the channel having what is called regular conditional densities, but maybe there are more general proofs available. Okay, so very nice. So even this wf is actually the density of the output measures WP with WQ. And therefore, just as we could write this guy as a divergence, we can write this guy also as a divergence. So therefore, Pxy is PQ hypercontractive implies dP of WP WQ is less than into P minus 1. So we'll take this guy this side. Actually, there is this 1 by Q power here, which must be brought down. So it's here, okay, because we don't need this 1 by Q power in dq. And so this is less than equal to, so this is P minus 1 by P, Q minus 1 by Q, dq, pq. So the only difference between this and the hypercontractivity statement is that hypercontractivity it holds for all function, and this one only holds for functions which can be expressed as these densities, which means they must be normalized to 1. But note that hypercontractivity, the hypercontractivity inequality is homogeneous. If you divide both sides, if you replace a function f with c times f, the inequality continues to hold. Therefore, we can always normalize. So this is actually if and only if is PQ hypercontractive. I'll just replace it with if and only if condition. If and only if for all Q that have density with respect to P such that d P PQ is finite, d WP WQ is less than equal to 1 minus 1 by Q by 1 minus 1 by P into dq pq. Okay, this is the same as, this is exactly equivalent to hypercontractivity. That's what we are claiming. Okay, this is not so clean. Okay, so this is hypercontractivity. So what is important here is that if you look at this constant here, this part here, this part here, this is less than 1 if if 1 by Q is greater than 1 by P, if Q is less than P. Okay, so if you can show that, if we show that SP xy is less than 1, then the data processing inequality holds with this constant less than 1. By the way, if Q is less than P, this dqp is actually an increasing function of non-decreasing function of Q or order alpha, and therefore thus dp wp wq is less than equal to c q times dq this, and which is less than, because this is less than 1, so this guy is also less than 1. This is less than dq q, which is less than equal to dp pq. Okay, or alternatively dp Okay, and therefore this is the data processing inequality we saw earlier, except that this constant can be made less than 1. And when is this constant the smallest? This constant is the smallest when this guy is the smallest. That's the best we can do. Okay. Note that SP is not exactly this guy. SP is related to Q by P. This is Q minus 1. This is slightly different but a related quantity. Okay. And in fact, there's a lot of work on connection between the best data processing constant, which is obtained by taking soup over this CQ here, and, which is obtained by minimizing over the CQ here, and this SPXY. Mostly this guy is attained when P goes to infinity. Okay, and that quantity coincides with the best data processing constant. That's usually the case. But here is an exact equivalent. So at Pxy is Pq hypercontractive if this Rényi divergence of order P satisfies this particular strong data processing inequality. The Rényi divergence of order P between Wp and Wq is less than or equal to 1 minus 1 by Q by 1 minus 1 by P dq pq. Okay. Okay. So this is another alternative form of hypercontractivity. So in conclusion, we have seen that hypercontractivity is actually equivalent to strong data processing inequality for any divergence. We have also seen two different forms of hypercontractivity. We have seen tensorization, which says that it suffices to show hypercontractivity for one dimension, and then you will automatically get it for any arbitrary dimension. In proving this equivalence of hypercontractivity and strong data processing inequality for Rényi divergence, along the way we remarked that it suffices to show hypercontractivity for functions which are normalized in any norm. In fact, if that inequality holds for f, it must also hold for CF. So this is all I wanted to say about hypercontractivity different form.